So today we shall continue our discussion on generative modeling. In last two classes, we discussed the background we need to understand the generative modeling. Today we shall hopefully finish generative modeling, and then we shall start discussing our linear models, the discriminative models. Now we are studying the generative models. That means we will be able to model the actual probability distribution, and we are interested in really understanding the distribution of the data. For discriminative models, we are mainly interested in how to discriminate or how to find different classes. But for generative modeling, we are more interested in finding the actual probability distribution of the of our data set, and then based on the probability distribution, we can classify. So we started with this example. We started with this example here. We have in the example, we'll be given a bottle of wine with a missing label, and here label could be either 1, 2, or 3, and these 3 are IDs for 3 different wineries. And a bottle is given means we'll get these 13 features for the wine of that bottle. So these are the 13 features. And then based on these 13 features, we are interested in modeling the probability for those wineries. And then after getting a new bottle based on those features, we want to classify the bottle. In the training set, there are 130 bottles, and in the training set, there are 43 bottles from winery 1, 51 bottles from winery 2, and 36 bottles from winery 3. So from these we get the class weights or prior. Prior means even if we have nothing and we are presented with a bottle without any features, what is the probability that it is coming from winery 1? In that case, because we have no data for the new bottle, our only information we have is the prior probability. That means if we don't know anything, and if we get a new bottle with probability 0.33, we'll tell it that it came from winery 1. With probability 0.39, we'll say that it came from winery 2. Or with probability 0.28, we'll say that it came from winery 3. Of course, we will not just state that probabilities. Maybe we'll use these probabilities to somehow classify it, but that will be our only information. That's why they are called prior or class weights. Now these are the 13 features again. So how can we find a probability distribution for different wineries? Basically, we will have to come up with a probability distribution. So it's not that we test different probability distribution. We can, but the normal procedure is to somehow use some intuition. Maybe it will fit Gaussian distribution, for example, and then we'll find the parameters for this distribution from the data set. For example, from the winery data, if we plot the feature values for alcohol level, and then we'll get a graph like this. So this is the graph we'll find for this data set. Now, obviously, the data set is not telling that it came from a Gaussian distribution, but we can argue that yes, but we don't have enough data. The data shows some early formation of Gaussian distribution, and if we had more data, or if we add more data, maybe it will look more like Gaussian than any other distributions, because already with this little amount of data, it is showing an early sign of being from Gaussian distribution. So it's like that, from some intuition, and then we can fit our data set to a Gaussian distribution. Or if it looks like another distribution, then we can fit to another distribution. But the main thing is, whatever distribution we choose, we need to find parameters for that distribution from our data set. So whatever data set we have, we'll have to find the parameters for our interested distributions that we want to fit to our data. Now, if we think that the Gaussian distribution is okay, then we need to find out two parameters, the mean and the covariance, or in this case, it is just using one variable, so mean and variance. So that's all. And if you can find the mean and variance, then we have everything to fit our data to a Gaussian distribution. For this distribution, we need, this is the density function for this distribution. Now, in this distribution function, we'll see that pi, it's a constant. Then we need the variance, and then e to the power minus x minus mu. X is our data, the data set we have. Mu, again, this is the mean, and again, this is the variance. So for this density equation, we need three things: our data set, mean, and variance. And if we have all these things, this distribution is completely defined. So we'll use our data set, and then we'll find the parameters, and then we can fit our data set to Gaussian distribution. Now, because our original data set came from three wineries, we'll find three different probability distributions. So if we plot for alcohol level, then this could be winery 1, this could be winery 2, and this could be winery 3. So we used our data set and then found mu1 for winery from winery 1. This was the mean alcohol level for winery 3. This was the mean alcohol level for winery 3. This was the mean alcohol level. And then the variance. Based on the variance, this curve will spread more or less based on the variance value. Now, the author who basically ran this experiment, he found that the test error becomes 29% if he used only one feature. So this is a case for univariate Gaussian, just using one variable. That's how we see this is the variable, and this is the density value. Now, 29% error is really huge. So the author also tested with more features. For example, then he tried two features, and for two features, at first he used alcohol level, and then he used flavonoids level. And after he used two features, he found that the error drops from 29% to 8%. So that means we need to be able to use not only univariate Gaussian, but also multivariate Gaussian. So it's showing early promise. So this is how we choose more and more complex model in our work. So we start with some really simple model or simple thing to do, and we check the error rate or other metrics also. Not only error rate, nowadays people use many different metrics, but based on the metrics we decide if is it enough. If it's not enough, we go either we collect more data or we use more complex models. So if we use multivariate Gaussian for 2 variable, it looks like this. So this is the alcohol level, Flavanoids level, and this is the density. So already it is looking complex. Now, if we want to plot it for more than 3 dimensions, we can't. For more than two features, we cannot, because if you use 3 features, then we really don't have an access to show the density value. We can imagine inside our head, but there are no ways we can draw it. Even interpreting this 2-dimensional plot is really hard because the values are hard to map. That's why I normally use contour plot. So contour plot means we virtually cut through a parallel plane and parallel to the here XY or alcohol and flavonoid level, those 2 axes, or the plane formed by these 2 axes, and then we cut these density values with parallel lines, and the intersecting edge we draw it. We draw in the base, and then we get a plot like this. That's called contour plot. So basically we want to interpret. So if it's really steep level, then we'll find very closely formed contour plot. If it's like flat, then we'll find contour plots that are far away from one another. So basically we get the idea about the distribution from the contour plot, but it's easier to interpret. For example, maybe we'll get contour plot like this for using 2 different feature values. Now, if we use 2 different features, that means the mu is no longer a scalar number, it's a vector. Similarly, the covariance, the variance is not present now. Now, because we have more than one feature, we'll use covariance matrix. And the covariance matrix will be a square matrix, and it will have values for covariance of all the combinations of feature values. So here we can say x, y. So all the feature values, all different combinations of them will have a covariance value in the matrix, and this is our mean value. So now we'll review some of the things that we already discussed. Suppose we have a feature x1 and its mean is mu1, and we have another feature x2 and its mean is mu2. So now if we want to measure the dependence between them, we can use either covariance or correlation. Now we use covariance when we are also interested in the scale. We use correlation when we are only interested in the relation. So we standardize the value of covariance and force the values to be only in the range of 0 to 1. Then we call it correlation. But if we are interested in scale also, then we use covariance. In this case, we are also interested in scale. So we use the covariance, and we know the covariance formula is this. So how these two features, they move around their mean. Do they move simultaneously or asynchronously? We want to measure that one. But we can also formulate this equation to interpret them in an easier way, like this. So they'll give the same values. Now, this value is maximized when x1 equals x2. That means when it converges to variance. And the maximum value covariance can have is standard deviation of x1 times standard deviation of x2 and plus minus. So we can say either max or mean, or basically the absolute value. This is the maximum range, either positive or negative. So we only discussed the nature of the values we have inside the covariance matrix.
Sir.
Yes.
Sir, can you repeat it again, or like I mean define it with some examples? I find it very complex to understand this part.
Okay, so we are talking about multivariate Gaussian distribution, something like that. Now, if we want to define multivariate Gaussian distribution, we define it using a vector mu. It's a vector, and covariance matrix. It's a matrix. Now, this covariance matrix, it has entries for how the features are related. For example, if we have only two features, but suppose we have a not a Gaussian distribution with two features only, but maybe we have with four features. And then the covariance matrix will hold the covariance value for all kind of relations between these four features. For example, it will have covariance of x1, x1, covariance of x1, x2, covariance of x1, x3, and covariance of x1, x4. Similarly, covariance of x2, x1, covariance of x2, x2, covariance of x2, x4, and finally here covariance of x4, x1, covariance of x4, x2, covariance of x2, x4, x4. So it will have a covariance matrix like this. Now this covariance matrix, they are holding all kind of dependency relationship between the features, right? We know that the covariance can measure the dependence between two random variables, right?
Yes, sir.
So they are
these dependency relationships. Will this always be like expressed by these matrices, right?
Yes.
Okay.
And then
sir,
yes.
Yeah. And sir, if like the matrix is like two-dimensional, does this mean like there are two features or things like that? I mean, if there are
matrix is two-dimensional, but we have values for all possible combinations of the features.
Okay.
So we have like here x1, 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 x2, x1, x3, x1, x4, and so on. And in the final row, maybe xn, x1, xn, x2, until xn, xn. So x are the features here. So in this matrix, it is two-dimensional, but we have it is two-dimensional because we are only modeling the dependency between two features only. And for that, we need like these square terms. And to keep these square terms, we can use a matrix of dimension d by d. Maybe it's really hard to understand. I'm giving you some time to think. And if you have any more questions, you can ask.
Okay, sir. Thank you. I think I understand now.
Okay, all of you, I'm giving you some time to think, just 2 minutes. Think over it, and if something is not clear, you can ask questions. And also remember the mu vector, it will contain all the mean values for the features. So it will have d numbers, one for each feature. So it will contain values like mu1, mu2 until mu d. Okay, I hope it's clear now. And then we'll.
স্যার
Yes.
স্যার আমরা যে গসিয়ান ভেক্টরটা নিয়ে আলোচনা করতেছিলাম এটা কি 3D?
This is basically 4D.
আচ্ছা
This one is 4D.
আচ্ছা আচ্ছা এখানে
So-
কয়টা প্যারামিটার নিয়ে আমরা আলোচনা করতেছি?
So for 4D, we'll have like 4 times 4. So 16 covariance value and 4 mean values. So in total, we'll have 14 parameters. In general, normally we have like for d-dimensional Gaussian distribution, we use d-square covariance matrix, d-square values for covariances, and d values for mean. So basically order of d-square, order of number of features.
তাহলে এটা তো 20টা প্যারামিটার তাই না? 16 আর 4
16 plus 4, 20, sorry. So basically the complexity should be order of number of features square, order of d square.
ঠিক আছে স্যার।
Okay, I'll give you a 3 minutes break for the Ajahn. Then I'll start again. Okay. So we talked about a 4D Gaussian distribution. Now it will be easier for us to understand two-dimensional Gaussian distribution. So for this two-dimensional Gaussian distribution, we see that we have a mean vector and a covariance matrix. Now, in this covariance matrix, the diagonal terms, they represent the variance values. Because for the diagonal terms, you have covariance of xi, xi. It is basically variance of xi. So the diagonal entries, they represent the variance. And of the diagonal entries, basically it's a symmetric matrix. It's a square matrix. It's a symmetric matrix because of the diagonal entries will have like x2, x1, and then here x1, x2, and then here we'll have x2, x1. So it's a symmetric matrix. And also they are the covariance values between features. Now here we see the contour plot, and in this contour plot, this could be for variance of one feature, axis of one feature, maybe sigma 1 square, and this could be the variance for another feature, sigma 2 square, and they are a little bit tilted. That means they have some covariance values. They are correlated. The features are not independent. They are somehow dependent. That's why we get some values here, and they will be a little bit tilted, or they will show some relationship. So we already discussed this slide. If you have any question for this slide, you can ask now. Otherwise, I'll skip it. This slide only discusses the properties of the covariance matrix. Okay, so for bivariate Gaussian case, again, there will be only two features. Mean, the dimension of the mean vector will be 2 by 1, and the mu1 is the expectation for the features of features x1, and the another element of mean vector mu2, it will be the expectation of the other feature, and then they will have a covariance matrix like this. Again, this one and this one, they are just the variance. And of the diagonal entries, they are really the covariance values. And density is highest at the mean, and it falls off in ellipsoidal contours. So that's why we saw a plot like this. Most of the densities are around the mean values. The more we go further from the mean, the density values fall. The density values fall exponentially. Any questions? Any questions? Okay. Now this is the equation for the density plot, density for bivariate Gaussian distribution. Again, we see here, instead of using sigma square, root of sigma square, basically sigma, we use the root value of the determinant matrix, determinant value of the covariance matrix. And then instead of using just the values, now we are using x t. It's not basically x, we can say it like x prime t, because we are changing x to x minus mu, then the covariance matrix inverse of it, and then x prime. Now if we are really careful in our previous class, we know this is a what? Can anyone tell this is what? We discussed only 6 days ago.
Sir, can you please repeat the question?
So I want to know what is this term, the green term that I just wrote. I want to know what is this term, what this term means. Okay, we discussed in our last class. This term, basically, if we expand that term, we get a quadratic function on x. So we get a quadratic function x, and the function evaluates to a scalar value, just one value. So the output of this operation or of this term is not a vector, it's not a matrix, it's just a scalar number. That's all. So in this case, the inverse of covariance matrix, it will contain the coefficient values for different quadratic terms for x. So we'll have quadratic terms like x1, x2, x1 square, x2, x3, all these quadratic terms. And this covariance matrix, the inverse of it, it will hold the coefficient values for these different terms. So here what we are doing is from the last point we are getting just a scalar number. So this will be like e to the power -5, e to the power -6, something like that. And this is a constant term, and this value will get a scalar number from the covariance matrix. So finally we are getting just a pure value for the density. That's what really expected. But inside this function, we are using all possible quadratic. We are combining all possible quadratic terms for the feature values. Now here we have only 2 features, but if we have more than 2 features, then we'll form the quadratic combination of all those features, and the covariance matrix, it will hold the coefficient for those values. So somehow we are getting a relationship from here. Some of the terms will give us large value. Some of the terms will give us smaller values. Some of the terms will be positive. Some of the terms will be negative. So based on that, we'll get some distribution like this. With high probability, the x values near the mean, they will produce high density, and the feature values far from the mean, they will produce low density values. So in other words, we are just trying to fit a distribution to our data set. We have 2 examples here. The first one, we see that the diagonal entries are pure numbers, but of the diagonal entries are 0. That means here the 2 features, this is feature 1 maybe, and this is feature 2, they are independent. That's why the covariance between these 2 features are 0. But they have some variance value. So maybe this is 4 variance value for one feature, x1, or for another feature, the variance is 1. But other than that, they have no relationships. But for figure 2, again, the same variance values, 4 and 1, but now the of the diagonal entries are not 0. They have positive values. That means these 2 features are not independent. They are somehow related, and these numbers are telling us the magnitude of that relationship. And that's why we see the ellipse now is a little bit tilted. So basically the tilt part, this angle is telling the magnitude of the relationship. So is it clear? I'm again giving you some time to think. If it's not clear, you can ask questions. Okay. So now we'll talk about decision boundary. So decision boundary, we use decision boundary to find basically classes. For example, here for three different wineries, and if we use only two features and we plot the values, maybe we'll get something like that. And we see here that if we draw boundaries like this, if we can draw boundaries like this, then we can use these boundaries to later for future classification. So if we get another point in future here, we'll classify it for this class, the red circle. If we get a new point here, we'll classify them for the green squares. And if we get a point here in future, we'll classify this as coming from the black triangle winery. So basically, we want to find out some simplifying boundaries, and then we can forget about the data. So these boundaries will give us our model. So at the end, after the learning process, we'll have a model. The model mainly will have some boundary rules, that's all. It can forget all the training data, but it must remember the boundary. Later on, we can just use the boundary for the classification. We do not need the training data anymore. So again, this is the case for bivariate Gaussian. So it is really important that we understand the Gaussian distribution properly, because even if we start using Gaussian distribution and start the training process, and if our underlying data, it really came from another distribution, but if we keep the training process and keep and try to train our model with more and more data, actually at some point it will converge to its actual distribution. So we can start from normal distribution or Gaussian distribution, and still we'll be able to find the actual distribution. So that's why we need to be very clear about the Gaussian distribution. Now let's talk about multivariate Gaussian. So from 2-dimensional to 10-dimensional. So in this case, basically d-dimensional. Now for d-dimensional Gaussian distribution, the mean vector, it will have d different numbers, one for each feature, and the covariance matrix will have d square entries, and its dimension will be d by d. And then the density function will look like this. Again, if we try to understand, so this is a constant value, and we are raising it to power d by 2, and then we are multiplying this term with the determinant of the covariance matrix raised to power half or square of it. So this is basically a constant term, or in other words, it's a normalizing term, so that it can normalize the values for a density plot. We know that density has some restrictions, value must be 0 to 1, something like that. So this constant term makes sure that we really get a density value. Only this part, it is dependent on our data set, because only this part contains x. But other than this term, everything is constant. That's why they are normalizing terms. And inside this, we have e to the power minus half, again another constant, and then this part. This part is really the variable part. So if we write here x minus mu, that means we are trying to standardize the variable. And we know this is a quadratic function. that give us a scalar value, and the scalar value will be of this all the quadratic terms of x minus mu vector. So we'll combine all the terms, but before combining, we'll standardize them by trying to make them centered around 0 values, x minus mu. That means we are trying to center the values around 0. And then we'll multiply the terms based on their covariances. So we are trying to understand if they are moving together or not. So we are taking hints from their correlations. So basically covariance, but with respect to relation, we can call them correlation. So we are trying to find out how they are moving with respect to one another. Are they moving together? Are they trying to moving independently? And we are doing it for all possible combination of all the features. So if we have d different features and we want to find relation between all of the pairs, we'll be able to combine them using d choose 2. So this is order of d square, and that's basically Gaussian distribution. So that's why it's so powerful. It is not ignoring the relationships between the features or among the features. And at the end of the day, the density value, it's a pure number. It's a real value. Now let's talk about some special cases, because we really want to find out different decision boundaries for Gaussian distributions using generative models. So one special case here, xi, they are basically features. Suppose the features are independent and they have different variance values. Then what will be the covariance matrix, and what is its inverse? So the covariance matrix, it will hold covariance between x1, x2, covariance between x1, x1, x2 until covariance of x1, x, d. Suppose this is a case for d-dimensional Gaussian. The second row should be covariance of x2, x1, covariance of x2, x2 until covariance of x2, xd. For the third row, it should be covariance of x3, x1, covariance of x3, x2, covariance of x3, x3, covariance of x3, xd. Finally, covariance of xd, x1, covariance of xd, xd. So just look at it for a couple of minutes, then I'll continue discussion. Make sure that you understand. Okay, hopefully it's clear now. Now we'll find the special case. So it's given that xi or the features are independent. If they are independent, that means other than the diagonal entries, all of the diagonal entries, they will be just 0, because independent. The features are independent. In other words, all these terms will be 0, all these terms will be 0. And then again, this will be sigma 1 square, sigma 2 square, sigma 3 square until sigma d square. Okay, I hope it's clear now. Now we need to find out the inverse of it. Now, because all the off-diagonal entries are 0, that means the inverse should be 1 by sigma 1 square until 1 by sigma d square. And these two,
স্যার
yes,
স্যার আমরা যখন প্রথমে ইয়ে করলাম যে কোভেরিয়েন্স x1 x2 তারপর x2 x1 এই পাশের গুলাও কি 0 হয়ে যাবে?
yes, everything will be 0 other than the diagonal entries, because all the features are independent. That independent means their covariance values will be 0.
আচ্ছা, তাহলে কি স্যার মানে এখান থেকে আমরা 0 ছাড়া আর কিছু পাচ্ছি না?
No, we get only the variance values. So the covariance between a variable with itself, it's basically the variance. We'll have variance values, but covariance will be 0 because they're independent. If two random variables they are independent, their covariance becomes 0.
আচ্ছা স্যার, আমরা ক্যালকুলেট করার সময় কি মানে ডায়াগোনালি যেগুলো নিয়ে নিছি এগুলা ইকুয়ালস 0 ধরে করব নাকি?
Say it again.
স্যার যেমন আপনি বললেন যে সিগমা 1 স্কয়ার 2 স্কয়ার তো এইভাবে সিগমা ডি স্কয়ার পর্যন্ত গেছে, এগুলা ইকুয়ালস কি আমরা 0 ধরে তারপর ক্যালকুলেশনটা করব?
We'll for the diagonal entries, the variance values are not 0, but all the covariance values they are 0, and the special case is the case here is that I is not equals j. That's all.
জি স্যার, ঠিক আছে।
Okay. Now this is the case for when we have the features are independent features. Now we'll talk about another special case, diagonal Gaussian. We'll talk about diagonal Gaussian. So here the features are again independent, one-dimensional, and basically it's the previous case. And for this special case, the density becomes even simpler. So if we simplify it, then we have a density like this. Now instead of using the covariance matrix, we can simplify it because we know only the diagonal entries are numbers and rest are 0. That means all the terms of the diagonal entries will go away. The only terms that will remain are related with the diagonal terms, and these are the terms here. Again, this is a quadratic function. We'll get a real value, and ultimately we'll have some constant e to the power minus some real value. Ultimately, this will give us a real value, the density value. And here, because the features are independent, the contours there will be axis aligned ellipsoids. They will not be tilted because they are not correlated. They are independent. Let's relax some more conditions. Suppose now we think that they are independent, the features, features are independent and all have the same variance. So now all these are 0, but the variance are same. Now, because variance are same, then our density function will even be more simpler. Basically, they are all same. That means they will have like sigma squared some term. Now we are taking inverse. So basically, it will be like 1 upon sigma squared and some value. And some value means just the difference between the actual data point and their mean values. And then we'll find concentric circles for different features. The contour plot will be something like this. Basically, they are distributed around mean mu, and for any axis, they have the same covariance values. To make sure that you understand. I hope it's clear now. Okay, now the question is, how do we fit a Gaussian to our data? So how do we fit Gaussian to our data? So for that, we just need two things, the mean value and the covariance matrix. And we can calculate from our data points using these two equations. So now back to the ordinary data. So the authors tested with two features, and they found this sort of boundary for two features, and the error rate dropped from 29% to 8%. And the author tested with all 13 features, and the test error rate ultimately went to almost 0. Now, we may think that if the test error rate goes to 0, it's a very good fit, but actually it's not. If the training or test errors sometimes become too close to 0, that means our model is too complicated. And it has so much capacity that it's memorizing the data set. For example, here, the ordinary data set the author used, it contained only data set for a couple of hundred something bottles. Now for such a small data set, using 13-dimensional Gaussian, that means the number of parameters should be 13 squared plus 13, around 182 or 80, something like this. Now with 182 parameters, and the data set size is smaller than this. So basically the model can memorize the data set. So if we become really excited that error rate dropped to almost 0, the model is so good, actually this is not the case. The model is memorizing the data set, but later when it will face more real world data set, maybe it will fail. Now, how do we classify using multivariate Gaussian? So after fitting different distributions to different wineries, so basically what we do, we find mean and variance for a data set. That means we find mean and variance for winery 1. We do the same for winery 2, and we do the same for winery 3. And then we fit a multivariate Gaussian for winery 1. So suppose I'm drawing for just one-dimensional case. Another multivariate Gaussian for winery 2, another Gaussian distribution for winery 3. And then we decide based on these 3 different distributions. That's why it's called generative model. At first, we find the distribution for different wineries, distribution for winery 1, 2, 3. And then when we get a new data point, we try it with winery. We try it with the distribution for winery 1. We try it for the distribution of winery 2, and we try it for winery of distribution 3. And whatever we get, whatever density value we get from winery 1, 2, or 3, we compare. And whatever distribution gives us the maximum value as the density, we take it granted. We label it based on that winery. Okay, now here we can simplify the term. For example, this is the term. Now, if we write S as this, and then we can simplify this term as this. So sometimes it becomes useful or helpful to write it in this form when we compare, because at the end of the classification process, we really just compare. And we can for 2 classes, we can do it using this term. So now the question comes, why we are using these 2 terms? So for 2 different wineries, maybe we'll fit the wineries to 2 different distributions. And here we say P1 and P2, 2 different distributions, and we'll also have some prior class probabilities. Now, if we use Bayesian for classification, then the probability for the new data point coming from winery 1 should be this. Probability of new data point X coming from distribution 2 will be this. Then we'll compare. And then we can use some simplification rules to compare. For example, here we have something like this. Now, if we take log of Px, we'll get like some constant term. We'll take log of this whole term. So it's a multiplication. So we'll get log of this plus log of this. Now this is a constant term. We can ignore it. Constant term plus e to the power something. So if we take log e to the power something, we get the power value, and power value is minus. So we'll get minus half x minus mu t x minus mu, something like that. That means if we ignore when we compare, we can ignore the constant values, because the constant values will be same for everyone. They do not contain any x values, but we'll compare only this term. And if we do that and do some calculations, we'll get something like this. So it's based on the x minus mu t x minus mu, that part only. We are taking log and then removing the term that are same for 2 sides. And then based on this, we get a condition like this. Here, this will be true if and only if this is true. Otherwise, so if this is not true, we have only one other case. We reverse the site. One of these. So we check for one of these. If this is true, then we classify new data point for class 1. If this is not true, we classify the new data point as this. Does it make sense?
No, sir.
Okay, look at the
Sir.
slide. Look at the slide and try to make sense, then ask questions.
স্যার কম্পারিজমটা আরেকবার একটু বলবেন?
So for the comparison,
কম্পারিজম আর হচ্ছে যে m দিয়ে where m equal to half এই দুটা হচ্ছে লাইন বুঝিয়ে দেন।
Okay, for the comparison, we have two different. We think that we already use some distributions to feed our data set. So we have two different distributions, one for class 1, another for class 2. Now, when we get a new data point, then we need to classify the new data point. How do we do it? We do it for class 1. The probability of the new data point should be class prior value times probability that it is coming from distribution 1. For class 2, for new data point x, the probability will be class probability prior times probability that it is coming from distribution 2. Does it make sense? So what is the probability that new data point coming from probability distribution 1? So it's basically probability of, for example, new data point is coming from distribution 1. It will be like probability of x equals 1 time probability of all classes times the prior value if we come from the base n. And now the denominator will be same for class 1 and class 2. That's why we are not using the denominator. We're only keeping the numerator. When we compare, we are removing the same terms from both sides. It still does not make sense. Okay, let me explain more. Probability of x given y. So when we want to find a class level for a bottle, what we are doing, what are we given? We are given some feature set, and we want to find the probability of the feature set. Given, we know the classes levels. Because this is really hard to find, then to make it easier, we try to find the probability values from the already fitted distribution. So basically, we are trying to find out the level and then a probability of the class level. But because the denominator, it's really hard to find. But fortunately, in this case, we are just comparing different classes, so we can ignore it. because this term will be same for everyone. So I can give it. We already have it in one of our previous lectures from the last class, how we derive the term. So it's basically coming from the base terms. So if you are interested, okay, let me go back to that slide again. So this was the slide. We used last time. So basically it's coming from here. So probability x, y. So xy means we have we want a joint distribution for the feature values and the levels. And then it will be like probability of y times, we know that probability of y times probability of x given y. So it's coming from the formula of the joint probability distribution or conditional probability distribution, like probability of A, B is equals probability of A given B times probability of B. A given B, that means given means it's already happened. That's why we are also multiplying its probability. Now, if we just use this formula for the joint distribution, then we do not need to think about the denominator. Do you know, we need to think about the denominator if we try to break down the joint distribution in two different ways. Now we are just breaking in one way, and then we are saying that the probability of y is the level here. Probability of y, this is the probability of a level. Probability of level means probability of coming from a certain winery. So this is called the prior probability. And then probability of x given y. So x given y, that means x given for the level, we have three levels here. So x given level 1, x given level 2, x given level 3. Three different levels. So for three different levels, we try three different distributions. But for binary cases, maybe we have two different distributions. So for two different levels, we'll try two different distributions. Then we'll have like probability of 1 x, and another one will have probability of 2x. Now does it make sense?
Yes, sir.
Everyone? If anyone has any confusion, you can ask now. I hope no more confusion. So I'll discuss again a little bit more. So here we are thinking that we have two different classes only for binary case. For two different cases, we are assuming that we have a probability distribution for class 1 and another probability distribution for class 2. Now, if we get a new data point X, we want to classify it. It should come either from class 2 or class 1. So the probability that it is coming from class 1 should be prior probability times the value we get as density from probability distribution 1, or prior probability 2 times the probability that it is probability density values from distribution 2. Now we'll get the values, and whatever value is larger, we'll assign that class to the new data point. And that's what we are doing here. Now, if we minimize this, we find a condition like this. How we minimize this? Basically, we take the logarithm of both sides and then use some algebraic tricks. So we'll get something like this. Now we'll only discuss from this because it will give us some intuition about the boundary, the decision boundary. In this term, we are using three different new symbols: M, W, and theta. So here M is this, W is this, and theta is a hyperparameter that we can find out using cross validation. But we are more interested in M and W because they define the decision boundary. We want to understand more how we get the decision boundary, because we want to know how the model really finds different classes. Now here M equals half of the difference between the two covariance matrix for feature 2 and for feature 1. And the W value, it's basically the difference between two vectors. So it is basically simple, but M, the difference between two matrices, it's mandatory to understand this to understand the decision boundary. Now we'll again look at some special cases to find out the decision boundary. For example, we have spherical Gaussian. The features we have, they are independent. That spherical Gaussian means the features are independent and they have same variance values. That's why they are concentric circles. Now for class 1, this is for class 1 and this is for class 2. And remember that we can have many features. We can have d different features. It doesn't matter. The main thing is we have two different classes. For example, in this case, 3 different wineries, but each of them have 13 different features. Now we are drawing for only 1 or 2 dimension most of the times, because we cannot draw for more than 2 dimensions. But they can have d features, but different classes. Now this is a case for 2 classes, but they can have, here we are discussing about only 2 features, but actually they can have any number of features, but we are drawing only for 2 features. Now for this spherical Gaussian, if we plot the if we take the contour plot, it will look like this. Now their decision boundary should be linear. Why? If we look at these 2 terms, the m, so we are taking the spherical Gaussian. That means we are thinking that the covariance matrix will have same values, so it will give us a 0. That means we'll have something like this only. But this is telling about mean. Mean should be same, because mean should be same, and we can check from the figure. Mean values have different magnitude, so mean values are not same. Only the covariance matrix, they are same, because they are independent. They have the same variance values. So we'll find a decision boundary based on this term only. So it's looking like wx minus theta equals 0, something like that, because at the boundary it will not be greater than, it will not be less than, it will be equals 0. So we know this is a equation for a linear line or linear plane. That means we will have a decision boundary that is linear. Now if we get a new data point here, we'll assign it class 1. If we have a data point here, we'll assign it class 2, like this. So so after we learn, if we only keep this equation for this line, using this line, we'll be able to classify any future data points, because we already discussed how we can find out the side of a new data point with respect to a line. So we'll get one side +1, another side will get -1. So after learning everything, the model should be really simple. Just a separating linear line. Now, what about we have class prior like this? Maybe we have class prior that says that probability for class 1 is larger than probability of class 2. Basically, then the line will shift maybe left or right. In this case, we shifted the line a little bit right. If the class prior are same, then it will intersect the middle, the difference between the mean, and then it will just intersect the midpoint. But if the class probability for class 1 is higher, then to accommodate more class probability, the separating line will move a little bit right, so that it can give more probability values for class 1. Similarly, if we had phi 1 is smaller than phi 2, then we'd shift the line a little bit left to accommodate the more probabilities of class 2. So the prior will not change the shape of the boundary, only it will change the location of the boundary. Now suppose they are non-spherical. That means they have different variance, but still they are independent. Because they are independent, again the m will be 0. That means the decision boundary will only depend on w, which is linear, which is basically will give us a equation like this. So wx minus theta is greater than equals 0. The boundary, the greater than equals, it's the condition, but the boundary is equal. Now this is again will give us a linear separating boundary, but now because they're non-spherical, so they'll be like concentric for different classes, but they will be tilted a little bit because they'll be elliptical. Because they'll be elliptical, then based on that, our separating line will have maybe different parameter values, but end of the day, it will again be linear. And also to accommodate the class priors, it can shift left or right. Now suppose we have different covariances. But in this case, we are using like they are independent, but they have different variance values. In fact, if that is the case, then this will not be 0 and this will not be 0. In that case, we may have a decision boundary like this. Now in this case, we tweaked a little more, like both of them have like a multiple of the identity matrix. And here we assume that the variance for 1 is larger than variance for 2. So you can see the larger variance here. But in this case, we'll have a decision boundary like this. So if we get a new point here, we'll assign it class 2. If we get a new point here, we'll assign it class 1. Again, if we have a data point here, we'll classify it as a class 1. So this is for 2-dimensional case. In 1-dimensional, they will look like this. To make it clear, to look like this. And in this case, for this part only, if we get a data point in this part, for classification, we'll assign them class 2. Other than that, this region or this region, we'll classify them as class 1. Now the general case. So it's basically we are to make the plot pretty, we did this, but this can be any irregular shape classes. So here one class has like they are from spherical Gaussian, another one is coming from diagonal Gaussian, and in that case normally we get a decision boundary like this. But whatever we do, we are getting some quadratic decision boundary because we are trying to model our classes using a distribution that is quadratic. So we'll get quadratic decision boundary. It's maybe coming from a parabola, a hyperparabola, or maybe some circles. And in very special case, we'll find some linear lines. But normally, they will be they'll have some they'll have shape of some form of quadratic form. And after training, we'll learn the quadratic function. And based on the quadratic function, we'll just find out the side for a new data point. So either it will be this side of the quadratic boundary or the other side. And we can find out which side it is. And then we can assign class level based on that. So if we think one side is plus, we'll get another side as minus. Clear? If something was not clear, you can ask questions. Okay, I'm going through the slide again. I'll not talk, just going slowly. From Okay, I'll start from here. So we only discussed for 2 classes. We'll be able to generalize it to more than 2 classes later. But for the simplicity of discussion, we used only 2 classes. So the first step was estimating the distribution for different classes. So if we have 10 different classes, we'll find 10 different distributions. How do we find the distributions? We'll find the parameters based on our data set for the distribution. And after that, we'll start classification. So we'll start this after we found the distributions for our data set. And then we'll start the classification. But for the classification, we'll have an estimation for the priors. Also, it is coming from the data set. And then also we have different distributions. And then we'll try to find the probability of the new data set for all different classes we have. And then we'll compare. Now we only have 2 classes. That's why we can use a comparison like this. Otherwise, we'll find the numbers and take the largest one. But for 2 different classes, we can minimize this relation to look like this. And this term has relationship for the covariance matrix and the mean values. And based on that, we can form different decision boundaries. Now, we can see that this is the quadratic term, as we know, xtmx. This is the quadratic term, and wtx. So it will contain only dot products between the weight values and the x. So it is a linear term, but this is the only quadratic term here, and it is related with m. Now this is m. So we see that the quadratic term will come if there are some if the features are not really independent. That means if we have some values for the or in other words, if the covariance matrix are not same. If they are not same, then we'll have some quadratic terms. Otherwise, we'll have only linear terms. Now this is the decision boundary. So if we have only linear terms, then the boundary will be linear, again linear, if these are cases where the covariance matrices are same. Now, if they are not same, then we'll have quadratic decision boundary, because then the term with m, they are not same, then we'll have some values for m. And if we have some values for m, then the decision boundary will have some quadratic term. There will be term like maybe x1 squared, x1, x2, maybe x3, x5, some terms like this. And for those terms, we'll have a quadratic boundary. Now, for the circle, we'll have only the x1 square, x2 square, or xd square, only those terms. That's why we'll find the decision boundary as circle. But if that is not the case, if they are completely different, then we'll have also terms for x1, x2, x3, x4, and for those terms, we'll have a parabolic boundary. Clear now? Okay, I think it's clear now. We'll move on. Now, what about multi-class classification? So for multi-class, we also do the same thing, exactly same thing. For k different classes, at first we find out the prior values for each class, and then we find the distribution for each defined class, and then when we get a new data point for classification, we find the probability value for, basically we are calculating the joint probability distribution for class 1, distribution of 1 new data point. So X is the new data point, and we do the same. So basically joint probability distributions X1, X2, probability of X coming from 3, prior distribution, prior probability of 3, and the density from the distribution fitted for class 3, and so on. So if we have k classes, pk, probability of k X coming from k, prior distribution of k, and the density value of kth distribution using X. Now we can get the values, real values from all these probability values, and then whatever value is the maximum, maybe this one, then we assign the class level for this, the maximum probability value. So maybe we'll assign 3. Now we can even simplify this. We can take the log of it, and if we take the log of it, it's because they are probability values, so they are less than 1. If we take log, normally we get a negative value but larger value. The absolute value is larger than the probability values. Then it becomes easier to classify, easier to basically compare. So the precision of the hardware matters less. That's why we sometimes take log, but normally it's our goal is to take the highest value for these probabilities, and we take the argmax. Argmax means the highest probability value we get for a certain argument. Here argument is 1, 2, or k. So again, if it depends on the decision boundary, it depends on the m and w values. So if somehow m becomes 0, we again get a linear decision boundary. If m is not 0, then we get decision boundary something like this, maybe something like this. Again, because m is not 0, then we get quadratic decision boundary. Okay, now we discussed fitting our data set to Gaussian distribution, and then using either joint probability distribution, which is basically a special case of Bayes formula, to find the actual class level from our data set. But the data set will not always follow a Gaussian distribution, and there are some cases where we may find better accuracy if we don't start from the Gaussian distribution. For example, maybe our data set has always positive values. Now the Gaussian distribution, it is defined from minus infinite to plus infinite. Now if our data set has only values only have positive values, that means 0 to positive infinite, then it's an overkill if we use a Gaussian distribution. So maybe then we can use gamma distribution. And gamma distribution does not only look like this. Sometimes you can find a gamma distribution that looks like this. So basically looks like a Gaussian, but only in the positive direction. Even we can form a gamma distribution like this. It's basically is coming from exponential distribution family. So chi-square distribution, it's a basically special case for gamma distribution. So this sometimes we may even find parameter for gamma distribution, and instead of using Gaussian, we can do everything for gamma distribution. if the data set is coming only for positive values. Now maybe our data set is like that. It has values for only values in certain range, for example 0 to 1, or maybe 2 to 3, or maybe 4 to 5, for example. In that case, even if you use gamma, it's an overkill, because gamma is defined for all the positive values. Now if all our data set is coming from has a range from 0 to 1, we better use some distributions like beta. So even if we have a distribution like uniform, beta can cover it, or a distribution like this, beta can cover it. But main thing is all the values must be in a certain range. Then we better use beta, and we can keep our calculations same. Like whatever we used whatever analysis we used for Gaussian, everything will hold, but we'll use gamma instead of Gaussian or beta instead of Gaussian. Again, we can have like these two will hold if we have a data set that is coming from continuous values. Now, if our data set, the values are not coming from a continuous distribution, but from a discrete distribution, like count, number of students attending classes during COVID, or number of patients being admitted to hospital during COVID, or during night, or during day, or number of vehicles we see on the roads during day, or number of vehicles blocked in a traffic junction, like this. Now all these are coming from discrete probability distributions. So in that case, maybe we should not use Gaussian, gamma, or beta. Better we should use some sort of distributions like Poisson distribution. So it just counts. Again, we can have another data set like for document classification, so some NLP problem. Then we cannot really count, but we need to use distribution for different word values. Maybe we can use bag of words or something, or count vectorizer, but that's categorical. So we can fit these distributions, and then again use the same analysis we did for the Gaussian distribution. So that means we are not only restricted to go to normal or Gaussian distribution, we can use any distribution that we think best fits our data set. But even if we start from Gaussian distribution, we'll find that end of the day, maybe it will come close to the original distribution our data set actually have. So this is the last slide for generative models. Next, we'll start our discussion on linear regression. So if you have any questions, you can ask now. Any questions? Okay, so if you don't have any questions, then I will stop presenting this slide now, and you can take a 15 minutes break. After that, we shall start discussing linear regression. Okay, now we shall start our linear regression. So we use linear regression to fit bunch of data points. So if we want to find some trend, or if we want to find if we want to fit our data and predict later, we use the data points like this. Maybe data points are like this, and we want to fit a line through the data points. So that's basically linear regression. For example, this is a data set of students' GPA. And this is the frequency. It is the histogram basically. Now, if we want to predict GPA for a random student from this group, how do we do it? So we have no other information. We only have this chart. We only have this chart. Then without any more information, our only way to predict something is based on the mean value. And in this case, the mean is 2.47. Because we have no other information. We only know about the population. We know nothing about a student or the features or anything. Now, if we do that, then what is the error for this prediction will be? Will be the actual GPA of the student for whom we predicted 2.47, and then the predicted GPA. The variance of this distribution will be 0.55. Now, suppose we have one feature, for example, SAT score. Now, in this graph, this axis, it plots the SAT score, and this axis, it plots the GPA of the student. Now, at least you have one more feature. Now, if you want to predict, what we'll do, suppose we want to predict at the beginning of student life. So then we have at least one feature, the SAT score. Now, if we already know the SAT score for a student, we'll take that, and then using the fitted line, we'll find the line, and based on the line, we can predict GPA for this student. And if we do it, the mean square error drops to 0.46. And if we have no information, then the variance will be the error. And if we have at least one feature, we see the error drops. Now the range is not huge, from only 0 to 4. So the reduction is significant if we use just one feature. So what we do, our data set will have some features, and based on the features, we'll have some points. And in these points, based on these feature values, we want to fit a line. Now, these feature values, they are called independent variable. And this is called dependent variable. We want to form a function or find a function of the independent variables, and the output should be a value for the dependent variable. So normally what we do, we plot some lines. We know that means our model here is a line. So our model is a line. And if we want to draw a line, we know that this is the equation for a line. And in this line, we have actually two parameters, A and B. And Y is the dependent variable, and X here is the independent variable. And A and B, they are the parameters we want to learn from the dataset. So if we draw a line like this, for example, we can have something like this. Now here for this graph, B is the intercept. Here B equals 1 and A equals slope. Here slope should be, the angle is negative, minus half. So this is the slope value. Now, if we can find A and B, we can find the model. That means we can find the line. Based on the values of an A and B, we'll get many different lines. We can find many different lines. So what we can do, we can, with this model, we can find any of these lines. Any of these lines. So whatever our whatever trend is present in our data set, if it can be interpreted by a straight line, we can do that. That's why we're telling that parameterizing a line. That means we just want to parameterize the line. So the line fitting problem becomes, formally we can define it like this. So pick a line among the all infinite possibilities based on parameters A and B. And here we have a data set x1, y1, x1, y2 until xn, yn. So coming from all are real, x are coming from a real, or all x are real numbers, and all y are real numbers. For example, x and y could be SAT score and GPA. So x is SAT score, GPA, SAT score, GPA. So this point, one SAT score, one value for SAT score, one value for GPA. Another data point, one value for SAT score, one value for GPA, and so on. For all these points, we can call them a tuple, somehow xi, yi. So all these points. And then we need to fit a line. That means what we do is y equals ax plus b. That means we find a model, and after we found the model, then for the new data set, for the testing data set, what we do, find the error value. Here, this is after we found the model for a new data point xi, we predict the value y hat, and this is the actual value. That means this is basically y minus y hat, which is as a loss value, and we take the square of it, because sometimes y will be larger than y will be larger, sometimes y will be smaller than y hat. So the larger and the smaller values will have a tendency to cancel each other. We don't want that, because if there is a loss, it's a loss, be it a positive or negative value, it's a loss. So we want to square it and then take the average of this loss. That's why we call it mean squared error. Basically, it's a squared error, but we are taking the mean for all our data points. That's why it's mean squared error. And this is the loss function. And we want to minimize this loss function. Why we want to minimize this loss function? If we think this is coming from our model, this is coming from our model. Now, if the actual value, and this is actual value, if the actual value always becomes close to the value we predicted, that means our model is performing a great job. That means the loss function will be minimized. In other words, to find a good model, we want to minimize this loss function. So the loss function can act as a guiding factor. It will guide us to find a model that gives us lowest possible error value or lowest possible loss value. Is it clear? Any questions? Okay. So basically, if you want to minimize the loss function, how do we do it? Any questions? Okay. So how can we minimize the loss value? So we can minimize the loss value using simple calculus. So one way is to use gradient descent function, and we'll discuss in detail the gradient descent function when we discuss neural networks. But here we'll use simple calculus. So we have a data set like this. We have a y value and different x values, feature values. And we have this equation. This is the loss value. Now, if we want to minimize this function, what we can do is take a derivative of this loss function based on a with respect to a, and take derivative of this loss function with respect to b. And when this becomes 0, this becomes 0, we minimize the loss function. We found the lowest value for loss function if we do this. How do we do it? So this is a convex function, and convex function look like this. Now this is the parameter space, for example a or b, and this is the loss value for this function. And it's a quadratic function. We know this is a quadratic function basically. Now if we take a derivative like this, then we really draw a slope at a point, and this is the value of slope at this point. And what is this point? This point is some parameter value. If it's a, maybe it's a1. So at point a1, this would be, this is the value, the tan theta of this, the tan of this angle. This is the gradient value. Now if it becomes 0, that means we are using this point. Now at this point it is not 0, it will have some value. But at this point, if we take derivative value with respect to this point, now it will be 0. And because it's 0, that means we cannot minimize it anymore. We already reached the minimum point for parameter, so that we can get the minimum possible loss value. Now if it is the plotting of this function, that means the lowest possible that we can achieve using this function is this. We cannot minimize more than this, and we can find this value by reaching this point. Is it clear? Any questions? I'm giving you some time to think. Okay, now if we do this, that means for this point it becomes 0. Now we can use this rule to find the value of a and b, so that we can get the minimum value for this loss function. That means we can find out the optimal parameter a and b, so that the loss function is minimized.
স্যার আমাদের স্কোয়ার্ড ইরোরটা কি জন্য লাগে? শুধু ইরোর হইলে তো না।
So we need squared error because let me discuss it here. So here this is coming from the model. So this is y hat or predicted value, and this is the actual value. So this is actual and this is predicted. Now we are taking the difference. So basically we're doing y minus y hat square. Why are we taking the square? Because y minus y hat will sometimes be positive and will be sometimes negative. And we are doing a sum here. That means if we sum up the values, some values are positive and some values are negative, they will cancel each other. Now we don't want them to be cancelled. Be it positive, be it negative. It's a loss value. So we must take the loss into our action. We cannot let the sum somehow compensate for the loss value and give us the magnitude of the loss as some smaller quantity. How can we do that? We can do it either by taking the absolute value so that we don't care about what it's positive or negative, or we can take the square value. So we can do both. Here we are taking the square value, and it's called mean squared error. If we take the absolute value, then it's called mean absolute error. Does it make sense now?
স্যার 1/n দেওয়া হয়েছে
And then we take the average. That's why you're taking the mean.
মিনের জন্য।
Yes, for taking the average, because if we don't take average, then the magnitude will depend on the data set. If we have lots of data points, we'll have a larger error. If we have only a few data points, we'll have smaller error. That shouldn't be the case. The error should be dependent on the model. It should not depend on the amount, the size of the data set we have. That's why we take the average. Does it make
স্লাইডে
sense?
যাবেন, প্রিভিয়াস স্লাইডে।
Do you have any questions here? Okay, I think no more questions here. So is this slide clear to everyone? Okay.
Yes, sir.
So now we will think how we can use simple calculus for finding the optimum value for A and B. So just to make clear, we really need to find out the optimum value for A and B so that this loss value is minimum. And we can find that because it's a convex function, and we can find this point for parameter value either A or B. And at this point, we know the derivative of loss value will be 0. So my pen is not going far, so here it will be 0. So if we want to do this, for example, this should be like at first sum, then we are talking about B. So this will be 0. And for this term, there will be a minus first, and then AX I plus B, and then Also, so the square is over the whole function, so it should be yi minus ax I plus b 2, and then for this part basically minus b, so it will be -1 equals 0. So do you understand why I'm doing this? If it's not clear, you can ask questions. Do you understand why I'm using this? Does it make sense? Okay, I hope you understood. Now, if we can just change the side because it's minus and there is another side, we can omit that 2, and the another side we can omit that, so it will become like sum of I equals 1 to n a x I plus b equals sum of I equals 1 to n phi I. So it will be like sum of I equals 1 to n a x I plus sum of I equals 1 to n b equals sum I equals to 1 to n phi I. From here we'll get like, this is like a constant value and we're summing it up n times. So nb should be I equals to 1 to n yi minus a sum I equals 1 to n xi. Now we can divide both sides by n. We get b equals 1 by n sum yi minus a 1 by n sum xi. Now this is we are summing up all the y values and dividing them by n. That means it's average values of y. Similarly, it's average value of x. So we are getting that the optimum value of b should be y bar minus x bar. Now we need the value for y. For that, I'll not do in the class. It's like you can think of it as homework. If you find out the derivative of loss value with respect to a, and it will not be related with b. So it will only depend on something like that, I think. X minus x bar, y minus y bar divided by sum of x minus x bar, something like that. So it will not depend on b. It will only depend on x and y. So our data set consists of only x and y. So we will be able to readily calculate this value. And this will be the optimum value of a, for which we'll get the minimum loss. And if we use this value here in this equation, then we'll get the optimum value for b, so that we can get the minimum loss value. And based on the value of a and b, we can find the model for the regression for this data set. Any questions? Okay, now so up until now we only talked about using one feature value. Actually, we'll have more than one feature value. For example, there is a data set. It's diabetic data set. It's called diabetic data set. This data set has 10 different feature values and some indicator or index value that can be used to measure progression of diabetic or of diabetics over the years. So this data set has a response y, or index or predictor for diabetics, and 10 different predictor variables. So how can we use that? So for using that, we use a different model. So in this model, we use all different features. And for different features, we use different coefficient or weight values. So end of the day, we use a model like this: Wx plus b equals some value. And then for finding out the parameters of W, we use a loss function similar to the earlier one we used. In that case, we use loss equals y, this is the actual value, minus W x plus b, the new model, and this is the y hat, and we take the square of it and then sum it up and then take the average. So basically we're using the same type of loss function, but now inside the loss function we are using a different model. And for this model we are using the data set, all the tuples were given. Previously it was r by r, now r d-dimensional r. That means the features have d different dimensions. That means we have d different features. And we'll get a singular value from this function because y has only one, it's a scalar value y. So we'll get the regression value for a new data point. Now this is called least squares regression because we want to find the least possible value for this loss value. That's our goal. Our goal is to find the minimum value or least possible value. That's why it's called least square regression. Now for diabetes data set, we have 10 different features. So now if we use just one feature, in that case we'll have a model like this: Ax plus b. We'll use just only one feature. Then the mean squared error comes like this value. Mean squared error, we find mean squared error as 3890 value. So the absolute value of mean squared error does not make much sense. It only makes sense when we have more than one values and we can compare them. For example, if we use two predictors, that means we use only two features, then we'll have model like W1x1 plus W2x2 plus b. So that will be our model, y equals this. So we are using two different features, and for two different features we'll have two different weight values or coefficients, and then the mean squared error becomes something like this number. So independently one number does not mean anything, but when you compare we see that the mean square error decreased or reduced, got reduced by using one more feature. So in that case this is a better model. This is a better model than this one. Now if we use all 10 features, then the mean square error drops to this number. So it's not a huge drop, but at least we can say that if you use 10 different predictors or all 10 features, the models become even better than using two different features. And then the model will look something like this: W1x1 plus W2x2 until W10x10 for different 10 features equals plus b equals 1. So that's how we model. And even that, in that case, when we use a model like this, model like this, we still can use least square regression. So the least square regression, basically the thing we used already, but we can minimize it and get a consistent form. Now we in this slide we have shown some tricks how to manipulate the equation for fitting it into standard mathematical format. But end of the day, our main goal is to minimize the loss value, and we can minimize the loss value using the gradient technique that we already discussed for finding parameters. Now instead of just a and b, we have a parameter vector, so we'll use vector and matrix operations, but previously we showed operations for only scalar values. So that's why we use some tricks so that we can fall it into standard techniques, so that we can use vector or matrix arithmetic, but the calculation are same, and they are conceptually the complete same thing. So basically our goal is to minimize this loss so that we can find the W vector, because it's a vector of d different numbers, and then we can take the dot product between different feature values and the W. So W dot X plus B equals Y. That's our goal. That's our model. And we want to find a model so that the loss function is minimum, and this is the loss function. It becomes minimized, and that solution is called least square solution. Now we have some questions like, if we find the minimum loss value, so we minimize the loss value as much as possible. So can we say that if we minimize the loss, it will be a great or good estimator for the future data set? Can we say that? So the answer is, actually we cannot say that. So if n is really large, then maybe, because if we can collect a very big data set, maybe it contains most of the population properties. So maybe we'll if we build a model using that large data set, in future we'll get better performance. But otherwise, we really cannot. Then how can we improve the performance of future prediction? Because to build a model, we are not really interested in getting performance for the training data set. We are more interested in getting performance for the future data set. So how can we do that? So for example, here, if we want to predict, now, for example, we have only one data point. Now for only one data point, we can find infinite number of lines. All of them will have zero training error. So that does not mean that for future data set we'll always get zero loss value, because we just have we have a very small data set containing only one point. Even if we have two data points, we can form a line having zero training error. But for future data points, maybe they'll be here and there, here and there. This model will have large loss value. But if we have lots of data points like this, maybe we'll get something that can represent the future a better way. So one way to find a better estimator is to use k-fold cross validation. We discussed about k-fold cross validation in when we discussed nearest neighbor algorithm. So in k-fold cross validation, we divide our training data set into k different subsets. set 1, set 2, set 3 until k different subsets. And then we training our model based on k minus 1 subset. So basically k minus 1, and then test it on the remaining subset. And for the next phase, maybe we'll keep this subset as test, and we'll train our model using rest of the subsets and so on. So if we do that, then there is a better chance that the statistics present in the dataset will be captured by the model, and then we can test it. So that is one way to find a better estimate, because we want to capture the actual distribution of the population as much as possible. Now, if we divide our dataset into smaller chunks, maybe some of the chunks will capture the variability in the model, and then we'll be able to extract that by training on smaller chunks and testing with another chunk. But the problem is, in that case, we have to train a lot. Like for k different subsets, we'll have to train n times. So it is at least n times more costly for CPU. Okay, I'll stop here today. I'll discuss something about our projects, and then I'll continue from here in our next class. So in our next class, for the first half, we'll discuss the content or topic for this course, and then you'll present your idea.